Let's kick things off with Section 1, the brain's hidden battle, taking a microscopic view.
So starting at the macro level, neurodegeneration is definitely not a simple one-size-fits-all process. The sources point out that conditions like Parkinson's, Alzheimer's, and Huntington's actually arise from a super complex web of factors. We're talking environmental triggers like toxins, genetic susceptibilities, massive oxidative stress that messes with our mitochondria, and, of course, the dangerous accumulation of mutant misfolded proteins. But here's the kicker. While all these factors play huge roles across different diseases, researchers are discovering that they often converge on one shared underlying molecular culprit.
That brings us to Section 2, the DNA dimmer switch. We're zooming way into the cell now.
To find that shared molecular culprit, we have to zoom way in to meet something called the histone. Now get this, if you stretched out the DNA inside just one single cell, it would be about 2 meters long. To fit all of that inside a microscopic cell nucleus, it has to be packed incredibly efficiently. So think of your DNA as a massive, continuous instruction manual for keeping the cell alive. Histones? Well, they're basically the microscopic protein spools that keep those miles of instructions neatly wound up and organized.
Now, here's where we see that biological dimmer switch in action. Cells use these little chemical tags called acetyl groups to control just how tightly the DNA is wound around those histone spools. Think about 2 states. First, we have acetylation. This chemical tag relaxes the spool. The DNA kind of unspools just enough so the cell can actually read the genetic instructions, turning protective genes on and keeping the cell super healthy. But on the flip side, we have hypoacetylation. When those chemical tags are removed, the spool winds up incredibly tight. The survival genes are completely silenced, and the cell is left highly vulnerable. The dimmer switch has essentially been flipped off.
Moving right along to Section 3, hypoacetylation. Let's decode this switch. The absolute crucial point here is understanding exactly what happens when this switch gets stuck in the dark. Let's break this complex term down a bit. Hypo simply means under, or less than normal, right? So histone hypoacetylation just means there are way too few of those relaxing chemical tags on our DNA spools. When this happens, the DNA is locked down. It's kind of like locking the blueprints to your house inside a safe where the builders can't even reach them. The cell's machinery physically cannot access or read the survival and repair genes it desperately needs to protect itself.
And this really backs up the hard science behind our metaphor. This quote, pulled straight from research on Huntington's disease, shows exactly what happens when the dimmer goes down. It says, decreased acetylated histone H3 is associated with down-regulated gene expression. Okay, in plain English, no tags equals no gene activity. The lights go completely out and the brain cell totally loses its ability to defend itself. Which leads us to Section 4, genes go dark. Let's look at the pathogenic cascade.
Let's see how this genetic darkness actually allows toxic invaders to destroy the cell, starting with the Alzheimer's cascade. The sources detail how a very specific enzyme called HDAC6 essentially goes into overdrive. You can think of HDAC6 as a biological eraser. Literally, its only job is to remove those relaxing acetyl tags from the histones. So, when HDAC6 is overexpressed, widespread histone hypoacetylation occurs. The DNA spools tighten up, and that shuts down the protective chaperone proteins, like HSP90, that normally act as the cell's cleanup crew for garbage. Without that cleanup crew, pathological tau protein tangles just pile up in the brain, literally suffocating the neurons.
And we see a really similar dark cascade in Huntington's disease, but triggered by something else entirely. Here, a toxic mutant protein called mutant huntingtin, or HTT, invades the cell. It physically latches on to a crucial helper protein called CBP. Now, CBP's normal, everyday job is to actually add those relaxing tags to the histones. But the mutant protein basically blockades CBP from doing its job. The result? You guessed it. Histone hypoacetylation. The DNA spools tighten relentlessly around histone H4, plunging those absolutely vital protective heat shock genes into darkness.
It is absolutely astonishing, honestly, to realize that this tiny chemical tag on a microscopic protein spool dictates whether our neurons survive or succumb to neurodegeneration. Whether it's an overactive erasing enzyme in Alzheimer's or a toxic blocking protein in Huntington's, the end result is exactly the same. Those crucial protective genes are locked away. The lights just go out. But don't lose hope yet. Here is Section 5, turning lights on and restoring brain health. Because here is the incredible news. Scientists are actively developing ways to reach right into the cell and flip that switch back on. How?
by utilizing specialized drugs called HDAC inhibitors. Remember that pesky eraser enzyme we talked about, HDAC6? Well, these inhibitors basically block the erasers. By stopping the enzymes that cause all that excessive tightening, the histones naturally become reacetylated. The chemical tags return, the DNA spools relax, and this de-represses the transcription of protective genes, meaning the cell can finally read its survival manual again, rescuing the function of the neuron.
And the laboratory evidence highlighted in our sources is just striking. When researchers inhibit HDAC6 in Alzheimer's models, the brain's chaperone network wakes back up and clears out those toxic tau proteins so much more effectively. In mouse models of Huntington's disease, treating them with histone deacetylase inhibitors not only reverses the toxic gene expression caused by the mutant protein, but it actually leads to improved learning and memory. We are literally watching the lights come back on in the brain. It's a real game changer.
So I'm going to leave you with this provocative thought to ponder. We've seen just how critical histone hypoacetylation is across multiple totally devastating conditions. If we can truly master this biological dimmer switch, if we can figure out how to keep those DNA spools perfectly relaxed and those protective survival genes humming along, might we one day illuminate a cure for the most devastating mind-stealing diseases of our time? It is such a bright prospect for the future of neuroscience. Thank you so much for joining me on this explainer, and hey, keep your curiosity switched on.